Good evening. Thermodynamics Introduction. In previous chapter, we have studied thermal properties of matter. In this chapter, we shall study laws that govern thermal energy. We shall study the process where work is converted into heat and vice versa. In winter, when we rub our palms together, we feel warmer. Here, work done in rubbing produces the heat. Conversely, in a steam engine, the heat of the steam is used to do useful useful work in moving the positions pistons, which in turn rotate the wheels of the train. In physics, we need to define the notations of heat, temperature, work, etc. more carefully. Historically, it looks long time to arrive at the proper concept of heat. Before the modern picture, heat was regarded as a fine invisible fluids filling in pores of a substance on contact between a hot body and a cold body. The fluid called caloric followed from the colder to the hotter body. This is similar to what happens when a horizontal pipe connects two tanks containing water up to different heights. The flow continues until the levels of water in the two tanks are the same. Likewise, in the caloric position of heat follows until the caloric levels, that is temperature, equalize. In time, the picture of heat as a fluid was discarded in favor of the modern concept of heat as a form of energy. An important experiment in this connection was due to Benjamin Thomson, also known as Count Rumford, in 1798. He observed that boring of a brass cannon generated a lot of heat, indeed enough to boil water. More significantly, the amount of heat produced depended on the work done by the horses employed for turning the drill, but not on the sharpness of drill. In the caloric picture, a sharper drill would scoop out more heat fluid from the pores, but this was not observed. A most natural explanation of the observations was that heat was a form of energy, and the experiment demonstrated conversion of energy from form to another form, work to heat. Thermodynamics is the branch of physics that deals with the concept of heat and temperature and the interconversion of heat and forms of energy. Thermodynamics is a microscopic science. It deals with the bulk system and does not go into the molecular constitution of matter. In fact, its concept and laws were formulated in the 19th century before the molecular picture of matter was firmly established. Thermodynamic description involves relatively few macroscopic variables of the system, which are suggested by the common sense and can be usually measured directly. A microscopic description of a gas, for sample, for example, would involve specifying the coordinates and velocity of the huge number of molecules constituting the gas. The description in kinetic theory of gases is not so detailed, but it does involve molecular distribution of velocities. Thermodynamic description of a gas, on the other hand, avoids the molecular description altogether. Instead, the state of a gas in thermodynamics is specified by macroscopic variables such as pressure, volume, temperature, mass, and composition that are felt by our sense perceptions and are measurable. The distinction between mechanics and thermodynamics is worth bearing in mind. In mechanics, our interest is in the motion of particles or bodies under the action of forces and torques. Thermodynamics is not concerned with the motion of the same as whole. It is concerned with the internal macroscopic state of the body. When a bullet is fired from a gun, what changes is the mechanical state of the bullet, its kinetic energy in particular, not its temperature. When the bullet pierces a wood and stops, the kinetic energy of the bullet gets converted into heat, changing the temperature of the bullet and the surrounding layers of wood. Temperature is related to the energy of the internal disordered motion of the bullet, not to the motion of the bullet as a whole. Thermal equilibrium. Equilibrium in mechanics means that the net external force and torque on a system are zero. The term equilibrium in thermodynamics appear in different contexts. We say the state of a system is an equilibrium state if the macroscopic variables that characterize the system do not change in time. For example, a gas inside a closed rigid container, completely insulated from its surroundings with fixed values of pressure, volume, temperature, mass, and composition that do not change with time, is in a state of thermodynamic equilibrium. System A and B, two gases are separated by an adiabatic wall, an insulating wall that does not allow flow of heat. Second, the same system A and B are separated by a dithermic wall, a conducting wall that allows heat to flow from one to another. In this case, thermal equilibrium is attained in due course. In general, whether or not a system is in a state of equilibrium depends on the surroundings and the nature of the wall that separates the system from the surroundings.